This is Dr. Carroll. Today's video is about binary trees. So to start the conversation off, let's talk about the abstract data type binary tree. So what is an abstract data type? The National Institutes of Standards and Technology definition I like a lot. And what it does is it focuses on the interface and not on the implementation. So an abstract data type focuses on the interface. What is a user of the method going to, what's it going to look like to them? So for a binary tree, let's talk about the operations that are going to happen on that. At the high level, we're going to need to create and destroy trees. We're going to need to add nodes into the tree and subtrees. We'll need to remove and we'll need to visit or traverse the tree and do something at each node. So let's first talk about creating. So we'll need to create an empty tree, and in an implementation that would look like a constructor most typically. We also might want to create a binary tree, abbreviated here BT, with one node already in there. For example, a root node, and that would also be a constructor. We also might know what the children are, and we might want to create a node with the root and the two subtrees. Again, a constructor method would be the implementation. Now the implementation is not part of the ADT here, but I'm just doing them side by side to help. We also would need to be able to destroy a binary tree and able to preserve memory. And of course, that would be implemented in a destructor. We might want to know if it's empty. We might have a method that is called isEmpty to implement that. Now let's talk about the accessors and mutators, the getters and setters. We might want to be able to modify the root's contents, the values in there. So we'd have a get root data and a set root data to be able to get at it. We need to be able to modify the children to add a left or a right child. And so we'll use the term attach left and attach right. So there's an existing subtree and we want to add it in. We might want to attach left or right subtree. Sorry. The attach left right is adding a node, whereas attach left right subtree is, of course, adding a subtree. We might need to remove a subtree. We'll call that detach left right subtree. We will need to be able to traverse the nodes, and now we might want to do it in pre-order, in-order, post-order according to our needs. And so we'd have a pre-order traversal, an in-order traversal, and a post-order traversal. Here I'm using set notation just to conserve space. So what's on the left, what's not in the square brackets, makes up the abstract data type for a binary tree. And in the square brackets is what it's going to look like more in an implementation. Okay, so let's look at a file. Here we have binary tree.h. Let's look at that. We're going to need to be able to handle tree exceptions and tree node. We'll come back to tree node and how that's defined. And we have our binary tree class here. Notice we have a constructor for an empty tree, for root item, for root with the trees, a destructor. We have our isEmpty, our getter, and our setters here. Notice it's virtual so that we're anticipating that it could be inherited and that we might want to overload it. And then we even have the protected methods here for methods that know about its implementation. Now we went over that really fast. I'd invite you to, this is on the class website, so I'd invite you to look through it more slowly. Here's the implementation. We have the binary tree class. The default constructor doesn't do anything really except set the root to null as appropriate. And then we have our other constructors here. And go through this on your own and understand it. Make sure you understand it and be able to recreate something along those lines. So let's talk about an example now. A binary tree. So here we have B as the root node, and then these other nodes. I did you like my ASCII art? So how could we build this binary tree with the methods that we specified above? Well, there's really multiple ways we could do it. We could create an empty tree and then just insert each node, or we could create a tree with a root node and then insert each node. I'm going to show you a way that uses more methods just to exercise them more for pedagogical reasons. Okay, so let's look at that. Again, this file is also available on the class website. Let's step through it. That was not stepping through it. Okay, here we're stepping through it. We're first going to create a tree, and we're going to give it the node B to start with. Okay, and so that's going to look something like this here. I'm going to create the tree as we go. Now, as we execute this next statement, we're going to create another node, BT2 here is what we'll call it. And that's analogous to I here, but there's no arrow yet. And then as we go to attach left and attach right, these are attached. And then we're going to create this node over here. Again, sorry, the drawing's not quite accurate. It's not attached yet. We're going to attach the subtree left here. And it's when we get down to here that we are attaching the subtrees, and then we have our complete tree. And then as we can go through the traversal then of the tree, we can go through it in pre-order, and we can call the display function here, which is just print out the item. And we can also do an in-order traversal and a post-order traversal. It'll look like that, and displaying the nodes. So now the question is, how are we going to do the implementation? Now that we talked about it in abstract terms, what's our implementation options? Well, we could have it array-based, and within the array-based option, we have two options. First, we could add tree nodes to the array as we go. Okay, we just have an array and just add them in. But if we do that, we need to be careful to keep a list of free nodes because there could be removals as we go. And the other option is use the structure of a complete tree and have the indices correspond to the positions of a complete tree, whether or not it's a complete tree. At this point, we're just talking about binary trees, so all binary trees could be represented by a complete tree with potentially missing nodes. For my ASCII art example here, we would need to have 6 nodes, and we would keep track of them in this fashion. And then we would store B in 0, I in 1, R in 2, N in 3, A in 4, and then Y in 5. And if we added another node here, we'd do it in 6, and then 7, 8, 9, 10, 11, 12, 13, 14, and so on. So we could just assume that the tree is complete and then add them. Now, if we remove I, for example, then we'd just leave this one. We would remove I and N and A, and would remove those and leave them empty. And then if they were added back in, then we would add them back in. Let's look at a file that implements this. Here we have this, again, this file is available on the class website. We need to specify how many nodes we're going to use because it's an array-based approach, okay? And here we're just going to say what we're storing is strings for simplicity. Really, we should template this, but it puts a lot less symbols on the screen. So here we have our private method. We're going to create a constructor here. It doesn't do anything except initialize the children. Also, this other constructor assumes that we know everything about the node, that we know what the node is and we know what the children are. And notice we're keeping track of the children as indices here. by ints. They're going to be stored in an array, here, this global array, and we'll just keep track of which index the children are at, okay? And then we add them in, is how we do it. Okay, so that would be tree-based approach. The array-based approach for a tree node. The other option is we could have a pointer-based implementation. So what would we need to change here if we were going to have a pointer-based one? We could get rid of the static number of nodes, and we need to change it from ints to pointers and ints to pointers, and then we can get rid of these globals. Let's see that. Here we got rid of the constant size, and now we're treating them as pointers with setting a default values of null in case they're not set. And then we keep track of tree node pointers here, and then there's no globals except the root global that we'd need to keep track of in some form or fashion. So and we just saw that file. It's available on the class website. So what are the advantages, disadvantages of the two implementation? Well, array-based allows for a very quick lookup. If you know the position of the node, you can jump right to it and you don't have to traverse through links to get there. But the pointer-based implementation allows for dynamic memory. Are we talking about 10 nodes? Are we talking about 10,000? Are we talking about 10 million? And those are very different situations, and so different implementations could call, different problems could call for different implementation. Also, the pointer-based implementation extends naturally to trees with more than 2 children per node, other than just binary trees. That's it for today's video.